Grid-based architectures, sometimes called clustered architectures or scale-out architectures, are based on scale-out as much as they are scale-up. And by scale-out we mean horizontally scalable, or adding more controllers to a single system but still having that system act as a single entity. Let's look at a picture or two to demonstrate the concept. We start out with a 2-node cluster or a 2-node grid array. Right now it looks exactly the same as our dual controller system. The fundamental difference here though is that we can add more and more nodes to this system as and when the system needs more capacity or performance. And by adding more nodes or more controllers, each time we're adding more CPU, more RAM, more connectivity and more storage capacity, allowing the system to scale out horizontally. And the important point here again, no matter how many controllers we have in our system, the system acts as a single image or a single system. So let's take our 2-controller grid storage array and scale it out horizontally by adding 2 more controllers. As we can see, these controllers bring their own CPU, RAM and disk drives to the party. And importantly, it's still a single array. But let's not be shy. Let's add another 2 controllers to the system, making it a 6-node system. Again, more CPU, more cache and more drives are brought to the party, but it's still managed and operates as a single array. It's brilliant. And other than the obvious benefits of scale-out architectures, such as simplified management, these architectures also bring better resiliency, and they enable us to ride out failure scenarios without suffering performance issues. Let's think back to our cache DIMM failure that we recently talked about, where our dual controller array had to switch to write-through mode. Now, let's re-evaluate this looking at our grid architecture. Let's say that each controller in our 6-node system had 16 gig of cache, giving us a total of 96 gig of cache across our 6 controllers. But remember, all cache is mirror protected for write data, so we'll only get 48 gigabytes of usable write cache. Anyway, let's say we lost a single controller, taking 16 gig of cache out of the game with it. Instead of simply going to write-through mode with its associated dire performance, this time the array will reduce the total amount of cache from 96 gigabytes to 80 gigabytes, and then divide this by 2 for write cache so that it's still mirror protected, giving us 40 gigs of mirrored write cache. And the grid array can do this because it still has 5 working controllers that it can mirror copies of write cache across in order to protect it. So any write data coming in to any one of the surviving controllers can still be protected to any one of the other 4 controllers. Importantly, this allows the array to continue to operate in high performance write back mode, albeit with 16 gigabytes less capacity to play with, but this is not the end of the world, and it's way better than having to lower itself to write through mode. Also on the topic of performance, a single node or controller in our 6-node grid system failing will only reduce the overall performance, the overall cache, network ports, CPU and the likes of the system by a sixth, roughly a reduction of 16%. 5 of the 6 nodes will still be up and working. This is far easier to take in your stride than the 50% performance reduction that you see anytime you have a failed controller in a dual controller array. This is a major advantage of grid architectures. It's also common for grid-style architectures to operate in true active-active mode, where more than one controller can own a LUN or volume and read and write simultaneously to it. An advantage of this is that all controllers in the array can shoulder an even amount of the overall performance load on the system. So, grid-based architectures tend to be much more evenly balanced. And now feels like a good time to introduce the concept of redundant networks. Obviously, each of our controllers is connected to a network so that its resources can be shared to hosts. However, this makes the network or the network card in the host a single point of failure. So in order to avoid this, we deploy dual redundant networks, as we now show in the slide. Each controller and each connected host is physically cabled to each of the 2 networks, meaning that if we lose a single network, the surviving network can keep us up and running. Okay, that's grid architectures. Let's now take a closer look at the back end of storage arrays.